I hope that also illustrates a little bit what has been happening all along. So you have your multiple shielding scheme with the input discretization, this discrete states that would live inside the NLP solver. And then the way you generate these functions f are via integrations that can, for example, be done by doing this. So on each of your SQP step, on each of your time interval, you need to basically unroll this code, generate all these little points. These are your S's. And that's one simulation. Then you restart the same code on the next point, generate that and that and that. And that builds all these tails in your NLP solver. And then you need to provide the sensitivities of that, and then you can take SQP steps. And you would have to do all these things at every SQP step. Okay. Yeah. Right. So now the question is, when you need to compute nabla G, you need to compute the derivatives of these guys. So essentially asking, if I move this point around, how will that point move around? And if I move my U, how will that point move around? And so it's about essentially trying to understand how changing the inputs in that code will eventually change the output. And you need essentially to unpack how these inputs will be processed in the code in order to understand how they will eventually impact the output of the code. And so that's the topic of algorithmic differentiation. And for a very simple code like this, it's not very hard to unpack what's happening. So I just made a little bit of room in my code to put a few more things, but the rest is pretty much the same. And so the way you should think of this is, here you basically have a long chain of expressions. So you take your S, it's initiated at xk, then you evaluate f on that xk, times this, plus s, and you replace. And you do that a number of times. So you can imagine, in some sense, the output of this code is basically f of a f of a f of a f, and so on and so forth. And each round of this loop will evaluate f on s that is itself made of s plus something times f, and so on. So you have like a Russian doll effect, right? So the way you unpack that is again via chain rule. So each of this replacement has to be chain ruled. And it's kind of the same as the variational approach, at least the same philosophy, because it's all about chain rules. But so essentially, you would build a matrix A that is essentially carrying the impact of the input xk to the code on your S at every step of the for loop. So at the very beginning, A is identity because S equals xk. So if you differentiate S with respect to xk, at the very beginning of the for loop, it's identity. But then S will become that, so you need to chain rule that to unpack how the next S is depending on xk. And you can do the computations for yourself offline, but essentially it looks like this. So at each round of this replacement, essentially you will have a transformation of your matrix A that looks like this. So identity plus this thing here. The identity is coming from the S, right? And this thing here is coming from this part. And what has happened here, essentially, it's very simple, is that you differentiate this thing here by xk, and that's what you get in here. And at the end of the for loop, the A you have in the end will actually, or actually the A transpose for this form here, will give you the sensitivity of f with respect to xk. Because at each round of the loop, this A is carrying the impact of xk on the S you currently have in your iteration. The B has the very similar thing. It's also looking like the variational approach. So it starts at 0 because UK does not impact S on the very beginning. S is given by xk. But as you proceed with these replacements, UK will impact S. And the way that happens is given by this. And again, that's a chain rule over U of this replacement thingy. So you have the impact of U via S and the direct impact of U on F. And actually it's important that you do it in that order. If you do the replacement of S first, then you will evaluate this expression on the new S, not on the old one, and that will screw up your computations. So you first compute the A and B's, and then the S. Okay, so essentially that will be an Euler integrator with algorithmic differentiation. And we call it forward sensitivities, essentially because these sensitivity computations are computed in the same way as the simulation. So as you generate the simulations, you also generate the sensitivities at the same time. Yeah, and the final B will give you the sensitivity with respect to U. Okay with that? Mm-hmm. So you get, in some sense, you get exact derivatives because your simulation is generated by this code, and all you're doing is evaluating the sensitivities of this code. So if this guy is very inaccurate and gives you a poor simulation, you still get the correct sensitivities. So if we do this picture again with this simple system, you may have poor integration accuracies. You still get very high or very accurate sensitivities. So that's a good outcome. Yeah, that's a remark. So algorithmic differentiation is not just about integrators. It's about any computer code that numerically evaluates something and how you compute the sensitivities of that of the output of the code. And you actually have softwares that, for example, can read through a C code and differentiate the C code and do that for you automatically. So you have quite powerful tools for doing these things. You could do the same exercise, for example, on an explicit Rugekunta 4 scheme. The RK4 is much more efficient than an Euler scheme. So for a given accuracy you want on your simulations, you would need less flops using an RK4 than using an Euler scheme. So in practice you would probably want to use these kind of things instead. And we don't need to go through the details, but if you wonder one day how you could code an RK4 with sensitivities, it's exactly the same principle. It's just you need to chain rule all the operations in the code and evaluate them. It would look like this. It's a bit barbarian, but it's not that hard to code in the end. And again, you have tools that do that for you, that you could, for example, Casari, you could code the integrator in a high-level language like MATLAB or Python, and just say, okay, that's my function. And then you can ask the toolbox to first can generate a C function that implements your integration efficiently. And then you can also ask, okay, also please generate the sensitivities of that code. And also as a C function, then you can get this without doing the work yourself, and have C functions that evaluate these things very quickly. So you don't need to do this yourself, but that's the way it would look like in the computer. Okay with that? Mm-hmm. Okay. Now I want to talk about another type of integrator than what we have seen here. Collocation-based integrator. So you have different types or classes of integrators, but that's one that is also quite used a lot in optimal control for a number of reasons. And this will be very strongly connected to the direct collocation method, and that also has connections to pseudospectral methods, so it's good to have a look at that. And it's not a very different story. It's just a different way of processing the integration of the dynamics. So now instead of, for example, using an RK scheme that builds the points one after another, like Euler, for example, you start from xk and you you build these little points S until you reach the tk plus 1. These guys will basically try to build a polynomial that approximates the trajectory decently well on the time interval, and use that to integrate the system instead. It's very useful, for example, if you have stiff dynamics, differential algebraic equations, and it's very useful in some applications that we could discuss about for a number of reasons. So well, here is the key idea. So this S of t, remember, that's the big picture. So you have one time interval, that's one tail in your multiple shooting approach. And you can imagine you have a vast number of these guys. You may have 50 of them on the right and on the left. That's one of them. So the initial conditions, these are variables in the NLP solver, and you need to build that trajectory that simulates the system on that time interval. And that's for one state. You may have a number of states. So that's your S, and you would, in collocation methods, want to approximate this S by polynomials of a certain order. And so the way it's done, you would start by picking time nodes inside your tk plus 1. So in that sense, you now have a time grid inside the time grid, right? You have the time grid T0, T1, T2, and so on. And now in each of these time grids, you select a finer time grid to work on your simulation. You can visually see here that the time grid is not uniform, and that's usually the case, that you should not choose a uniform time grid. Actually, you have some very specific rules on how to pick these points. Yeah. And so the way you will build your approximations, you'll basically select a family of polynomials. You can call them pki of t. So k is the index of the interval in which you are, on which of the tails you are, and I is the index of the polynomial. And then on each of these intervals here, you have a set of parameters. Let's call them theta, ki, and you make a linear combination of your polynomials to generate your trajectory here. So this S of t is basically parameterized by your thetas, and you can evaluate this S at any time instant. Okay with that picture? Maybe I can already say something about that. If you think of, for example, the Euler scheme of before, or any explicit integration scheme, they would basically generate points along this trajectory, right? And in principle, you have no idea of what's happening in between. When you build your scheme like this, you have a polynomial or a family of polynomial that give you the trajectory for all time. So you no longer have like discrete points along this trajectory, you have the full thing. So that's, for example, useful if you want to have an idea of what's happening at any arbitrary time point on your trajectories. The way you will select your polynomials, this pki, you will select them such that essentially these thetas become the checkpoints on the time grid. So you'll choose the polynomials such that when you evaluate this trajectory S for a given set of parameters on one of your time points, that it will go through the value you put in the parameters. So you could kind of think of now that what your thetas are the position of your polynomial on these points, and that you can move them around, and that the trajectory will follow what you're doing with these thetas. So that would be an example. My theta k0, 1, 2, 3, 4, and the polynomial I build will go through all these points. So if I move this guy down here, the whole thing will shape to follow that. It's fairly easy to select the polynomials to achieve that. You have the family of Lagrange polynomials. You can build them. don't see that very well. I will come back to this later in the direct collocation method, but essentially each of these polynomial is going through is 1 on one of the time nodes and 0 otherwise. So the red one is 1 here and 0 everywhere else, and this one is 1 here and 0 on all the other points, and so on and so forth. And that will by construction satisfy this. Okay, so that's the picture. Now you have 1, 2, 3, 4, 5 degrees of freedom. So essentially k plus 1, I chose a polynomial of order k. And now we have to essentially decide how we will choose this theta such that this blue thing here, the polynomial, is approximating the trajectories in a meaningful way. So the first thing you can obviously do is say, well, my initial condition is here, so it would make sense that my polynomial is starting here at this point. So you will say the polynomial at time tk, I want it to be at xk. That's the variable coming from the NLP solver. No? So that's one condition you have to could impose on your polynomial. And the other condition you will put is that on each of these time points, I want the polynomial to satisfy the differential equation. So the slope of my polynomial on this point, del over del t of this guy, should satisfy x dot equals f at this point. So I plug s in my f, and I want that to match the slope on that point. So on these discrete points, the polynomial satisfies the ODE. Okay with that? Mm-hmm. Okay, so basically your collocation-based integrator would try to enforce these constraints on the theta, and you have actually as many constraints as degrees of freedom. So these equations will define your thetas if you solve them and if everything is well posed. You can make a few transformations here. The first one is your S at tki, essentially one of these bubbles here. Huh? So that's the parameter itself at this point. So that's theta ki. For example, S at tk2 is theta k2. So I can replace this thing by theta ki. Right. This time derivative is trivial to take because S is this linear combination of the polynomial. So essentially you just move the time derivative of the over the polynomial. And this is given explicitly. It's a polynomial in t that is fixed. So you just need to time differentiate that polynomial, and you get an expression. Which means that you're basically doing that. You have this time derivative here equals this, and you have this initial condition. And if your first point in the time grid is coinciding with tk, then you can even reduce that to theta k0. So now you have a collection of equations in theta, and what you would do then is to deploy Newton to solve them for theta k. Maybe it's interesting to specify, so this equation is linear. It's just a linear combination of thetas. This is linear as well in theta. These are basically numbers. It's your polynomial's derivative at different time points. And this equation is nonlinear if your model equations are nonlinear. If you have a linear model, actually the whole system is linear. If you have a nonlinear model, then you need Newton to find the thetas. Okay with that? Yeah. So here's an example. If I, that would be the infinity norm of all these constraints. If I have some dynamic system behind this. If I was evaluating the collocation equations for this polynomial here, and as you iterate Newton, actually we don't see much. That's the starting point, and after one iteration, Newton is already nailing down the trajectories pretty much. These dashed lines here. And that's a fairly common feature with these collocation equations, that Usually it takes 1 or 2 Newton steps to nail down the thetas that generate the right simulation. Okay with that? Yeah, if you were to slow down the Newton iterations by reducing the steps, you will see something like this, so a convergence to the correct solution. And so you would have Newton like running behind the building of these tails, and once you nail the right thetas using Newton, to generate the function f that you're supposed to return to your NLP solver, you essentially have to evaluate this polynomial at the final time, so tk plus 1. So you basically take s evaluated at tk plus 1 over there, and that would give you the function f. Right, so it's essentially you get your thetas from Newton, and then you evaluate this thing here with these values here. That's your function f xk uk. So in the NLP solver, essentially you need to, or you could replace your shooting gap constraints by doing that, where the thetas are given by the Newton method. Make sense? Okay, now that's how you get the simulations. You can essentially communicate this the value of this constraint to your NLP solver. What is the actual state for a given xk? But the NLP solver will also want to know the sensitivities of this constraint. So it will want to have the derivative of f with respect to xk uk. Okay. Now it's a bit of a problem because f is given by this thing, which is function of the thetas, and the thetas are implicitly given by a set of equations, right? So essentially it's asking the question, if I was to change the initial conditions a bit and solve these guys again, how would the theta move, and as a result, how would the endpoint move? Does that make sense? So that's not a very obvious thing to do. So do you have any idea what tool you can use to compute these sensitivities? So you have the thetas implicitly given by some equations as a function of the xk's and uk's. And the question is, if I change the xk uk's, how the thetas will change accordingly?
Implicit differentiation?
Yeah, there is actually a mathematical name. Implicit function theorem. Have you heard about this guy? Yeah? No? Okay. It's good that we look at it. I'll not detail too much the theorem itself, just the conclusion essentially, or the practical outcome. Okay. So here's how it looks like. So you have a set of equations giving you your theta. Yeah, you have a number of them. You have this equation and k's of these equations here. So I goes from 1 to capital K. And really you should just look at them as, just pack them in a big vector and call it C. And essentially you have this set of constraints. You provide xk uk and you have to solve them, for example, via Newton to give you theta k. And in that sense, you should view theta k as a function of xk uk, because theta k is always adapted such that this holds. So if you were to change xk in these equations, you would need to change theta k accordingly, for example, for this to always be satisfied. So in that sense, theta k is an implicit function of xk uk through this set of constraints. Just a reminder, so Newton would essentially do that. He would take steps in the theta k by doing the usual stuff. So del c del theta. Theta is the unknown you want to solve for, minus 1 times the constraint. If you iterate that, maybe a bit carefully, maybe with reduced steps, that would give you the correct thetas. So the integrator is, or the outcome of the simulation is given by that. I evaluate the polynomial for the theta k solution of this thing up here at time tk plus 1. And so if you want to compute del f del xk and del f del uk, that's what you would return to the NLP solver. You could do a chain rule, huh? So it's actually del s, del theta, del x, del s, del theta, del u. So just chain ruling. So now the question is just to show that these things that you need to return to the NLP solver, essentially to build them, you need to calculate this guy. So how will theta be impacted by changing xk in these equations and theta by uk? This guy is, it's easy to differentiate. It's just differentiating this sum of this type here. So how do you compute the theta by x and theta by u? And that's where the implicit function theorem helps you. And I don't know if I have a marker or something. No, okay, I could have written down something. Okay, so the IFT, implicit function theorem, says that so that there will be a relationship between del theta del x and derivatives on the set of equations C, and that this thing must be 0 and that thing must be 0. That may sound a bit mysterious, but it's actually completely trivial, the reason why this should hold. It's essentially saying, yeah, it would be better to write it down, but maybe you can imagine it. So you would basically say that the total derivative of C with respect to x, for example, should be 0. So if I change x, theta will be changed accordingly by Newton, for example, such that this still holds. So if I change x, this would still be 0. So if I differentiate this thing with respect to x, but in a total derivative sense, that should be 0. And if I do a total derivative of this thing with respect to x, I would have del c del x, and the derivative of c with respect to x going through theta. So that's del c del theta del x. Right. So it's basically just an impact or an effect of the total derivative. Same story for you. So yeah, maybe next time I can write it down how it works. But we have this, and which means that if del c del theta is invertible, I can actually extract my del theta del x from these equations. I have this and I have that. And I can compute these guys, plug them in here, and then I get the sensitivities of my simulation. Any question on that? It's a bit of a big piece to swallow, but
so the implicit function theorem basically states that the total derivative is 0.
No. Okay, it states a lot more stuff. The IFT is essentially saying if you describe, for example, in this case, theta as an implicit function of xu via these equations, it's actually discussing what are the properties of this function, theta function of xu, given implicitly by this c. It's actually asking, is it continuous, is it differentiable, is it smooth, does it exist locally? So all these questions are impacting the theorem. So it's actually a pretty deep tool. But the practical consequence for us is this thing here, that you can actually do that and calculate the del theta del x, del theta del u by doing this transformation. And the IFT is very much based on the invertibility of this Jacobian. So if you're not singular on this thing here, then a number of properties hold for theta as a function of the other variables. So if you don't know the IFT, look it up. It's a very, very powerful tool in calculus. Okay, what is very interesting here is that if you think of, okay, how do I compute that in the computer in the end? Well, I need to form this matrix here and then multiply by this one. So forming that is not extremely crazy. It's differentiating c by x and by u. It's just calculus. So then you have to form this matrix and invert or factorize it. The good news is, in order to find your theta, you have run Newton, and you have basically ended up with factorization of this matrix at the theta you are interested in. And this thing here, you can keep it and plug it in these formulas here and get these sensitivities pretty much for free, right? So as opposed to, for example, using an RK4, for which if you want to build the sensitivities, you need to add all this AD stuff, right? Or the variational approach, you need to integrate all these A and B matrices along. With this type of integrators, it's a bit more expensive to run the integration because you need to run Newton, but once it's done, the sensitivities are for free, pretty much. It's just multiplying some matrices in the end. And this thing here is basically, you have it already because you needed it anyway in Newton. So yeah, that's the bottom line. You get the sensitivities more or less, not exactly for free, but for very cheap in these integrators. Okay with that? Okay, what time is it? Do you want to do a few more minutes or should we stop here? If you're tired, we should stop here because it's a bit hardcore. Okay. Yeah.